All right, welcome back, everyone. Ready for another deep dive?
Always.
Awesome. Today we're going to be tackling alternating current.
Or as the cool kids call it, AC.
You got it. So, you sent over alternating current.pdf. It's
a bit of a beast, isn't it?
yeah, a little dense, not going to lie, but that's what we're here for, to break it down.
Absolutely. Make it digestible. I think there's some real gems in there.
I think so, too. All right, so AC, it's the kind of current we use every day, right? In our homes, businesses, like everywhere. But I always wondered, what actually makes it different from direct current? Isn't it just, electricity flowing through wires?
Yeah, it is. But the way it flows is really the key difference. So with DC, like what you get from a battery.
Yeah, your classic battery.
Right. The flow is constant. It's just going in one direction.
Straightforward.
Yeah. But AC is, well, it's a bit more dynamic. It's constantly changing direction. Like it's oscillating back and forth. So instead of the steady stream, think of it more like a wave.
Okay, like a wave that's constantly going up and down.
Exactly. Constantly shifting between positive and negative values. And that wave-like motion, that's what gives AC its new properties.
And lets us do cool stuff, I guess.
You got it. Think about the power grid. It's AC's ability to change direction that lets us use transformers.
Yeah, those giant things you see on power lines.
Exactly. They step up the voltage so we can transmit it over long distances without losing too much energy.
So we can send power across, states and stuff.
Exactly. And then step it down again for safe use in our homes. That wouldn't be possible with DC.
Right. So, okay, but if AC is always, changing direction, doesn't that mean it kind of, averages out to zero over a full cycle,
Yeah, that's true. The average value over a cycle is 0. But that doesn't mean it has 0 power.
Right, because, my lights still turn on.
Exactly. That's where we need to introduce something called RMS, root mean square.
Oh, yeah, I remember seeing that in the PDF. Didn't quite
get it. So, think about it this way. The heat an appliance generates, that doesn't depend on whether the current is flowing forward or backward. It still gets hot, right?
Yeah, definitely. Especially my toaster.
Right. So the RMS value is basically the DC equivalent that would produce the same amount of heat.
So it's kind of like a way to measure how much it's actually doing, even if the average is 0.
Exactly. You can think of it as the real voltage or current that's doing the work. It's a way more practical way to think about it than just some, abstract math formula.
Okay, I think I'm getting that. RMS. Got it. So how does AC behave when it hits different components in a circuit? Does it flow the same way through everything?
Not at all. Every component interacts with AC a bit differently. Let's start with a simple resistor.
All right, classic resistor.
So in a DC circuit, a resistor basically limits the flow of current, right?
Yep, that's what they do.
With AC, it still does that, but now the voltage and the current, they both rise and fall together in sync with the AC waveform.
Oh, so they're kind of following the same wave pattern?
Yeah. We call this being in phase. The voltage and current are always in step.
Kind of like a synchronized swimming kind of thing.
Yeah, exactly. But this brings up an interesting point. If the average current over a cycle is 0, shouldn't the power consumption also be 0?
Oh, wait, you're right. But it's not, is it? Because,
Your toaster still works.
Yeah, exactly. So it must be that RMS thing again. It's the RMS values that determine the actual power.
You nailed it. Not the average values. The RMS values tell us the real power that's being used at any given moment.
This is all starting to click now. Awesome. Yeah. But I have to admit, thinking about all these changing values, it's starting to feel a bit complex.
Absolutely. It can get a bit tricky. That's why you have these handy tools called phasors, or visual aids that help us represent these AC quantities.
Yeah, phasor diagrams. I saw those in the source material, but they're not actual vectors, right? Stress that point.
Right. They're not physical vectors. They're just a tool to help us visualize what's going on. They help us see the phase differences between the voltage and current in different components.
Oh, okay. So when we start talking about inductors and capacitors and all that.
Exactly. But before we jump into those, there's an important point the source made about phasors. They're great for steady-state AC, where the frequency is constant, but they don't really tell us about how a circuit behaves when you first turn it on.
So they show us the main event, but not the setup.
That's a great way to put it. But with that in mind, let's start talking about how AC behaves with inductors and capacitors, shall we?
Yeah, let's do it. Inductors first, I guess.
Yeah. Inductors, they're kind of interesting. They have this tendency to resist changes in current flow,
Right.
almost like they're, trying to maintain the status quo.
Stubborn little things, huh?
Something like that. But the math, the current in an inductor actually lags behind the voltage by a specific amount, pi over 2.
Pi over 2, fancy.
Yeah, it's all about the angles. But this lag, it comes from something called Lenz's law, which basically says that an inductor, it's going to create a magnetic field to oppose any changes in the current flowing through it.
So they're like pushing back against any sudden shifts?
Yeah, that's what causes the current to lag behind the voltage in an inductor. It's this kind of like built-in braking system.
So inductors, they're like the stubborn ones, huh? Trying to keep things steady.
Yeah, they like their routine, but capacitors, they're kind of the opposite. They're like the eager beavers.
Oh, how so?
Well, they actually encourage current flow. They lead the voltage by pi over 2, actually.
Leading the voltage. So they're like ahead of the curve, kind of.
Yeah, that's a good way to think about it. It's because they store energy in an electric field.
Okay.
So when the voltage across a capacitor changes, it either absorbs or releases that energy. And that's what makes the current lead the voltage. Think of them like tiny little energy reservoirs, constantly charging and discharging.
So that back and forth, that's what puts the current ahead of the voltage.
You got it.
Yeah.
And it's really interesting how different that is from the way inductors behave.
Yeah, total opposites, it seems. One's holding back, the other's rushing ahead. So when you put them together, that must make things.
Interesting.
Yeah.
Definitely. But before we get to that, there's another thing about capacitors that's kind of like resistance.
Okay, I'm listening. Is this about impedance? I saw that word in the source material.
Yes, good catch. So resistance, it measures how much a component opposes DC current.
Yeah, the basic stuff.
Right. Well, in AC circuits, we have reactance. It measures the opposition to AC.
AC resistance, basically.
Exactly. And for a capacitor, that's called capacitive reactance.
Right, and so how does that work? What affects it?
Well, it's inversely proportional to the frequency of the AC and also to the capacitance itself.
So higher frequency, higher capacitance means less opposition.
You nailed it. Less opposition to that AC current flow. And then impedance, that brings it all together. Resistance, reactance, the whole shebang.
So it's like the total obstacle course for the AC current.
That's a great analogy. High impedance, tough course, lots of hurdles. Low impedance, smooth sailing.
Got it. So we've got our individual players. Now what happens when we put them all together in a circuit? Resistors, inductors, capacitors, all in the mix.
Things get interesting. That's what we call an LCR circuit. And they don't always play nice.
Because the inductor wants to do one thing, the capacitor wants to do the opposite.
Exactly. That tug of war between the inductive reactance and the capacitive reactance, it determines the overall impedance and the phase difference between voltage and current.
So it's like a constant battle for control.
Yeah, you could say that. And sometimes they actually cancel each other out. That's when you get resonance.
Resonance. I remember that term. Sounded kind of important.
It is. So at a specific frequency, the inductive and capacitive reactances, they perfectly balance. And that means minimum impedance, maximum current flow.
The circuit's like perfectly tuned right at that frequency.
You got it. It's like pushing a swing at just the right moment. Maximum height, minimum effort.
Okay, I'm getting that. And the source had some cool real-world examples too, right?
Tons. Think about tuning a radio. You're literally adjusting the resonant frequency of the circuit inside to match the frequency of the radio waves.
Wow, I never thought about it like that. So resonance is like everywhere.
It is. Wireless communication, medical imaging, it's a fundamental principle. Pretty cool, huh?
Yeah, definitely. So much more to these AC circuits than meets the eye. Speaking of which, there was this thing about power factor mentioned briefly in the source. It said that not all current contributes to actual work. I wasn't quite sure what that meant.
That's a good question. It can be a bit confusing. Imagine you're pushing a heavy box across a room.
All right, I'm pushing.
Now, you're putting in effort, right? But if you're not pushing in the right direction, you're not really going to get it very far.
So it's like wasted effort.
Exactly. In an AC circuit, the power factor tells us how much of the current is actually doing useful work.
Yeah.
Like actually powering something.
Like making my toaster toast.
Exactly. High power factor, most of the current is doing its job. Low power factor, lots of wasted current.
And I think it had something to do with phase differences, right? Inductors and capacitors messing things up again.
You're on a roll. Remember how inductors make the current lag and capacitors make it lead?
Yeah, that tug of war.
Right. That phase difference, it affects the power factor. If the voltage and current are in phase, like in a pure resistive circuit, the power factor is 1.
Yeah.
All the current is doing useful work.
Perfect efficiency.
But when you add inductors or capacitors, that phase difference, it throws things off, lowers the power factor.
So the more out of sync they are, the less efficient the whole thing becomes.
You got it. And there's this crazy thing the source pointed out about purely inductive or capacitive circuits. The power factor is actually 0.
0. But current is still flowing.
It is. But the energy is just being stored and released, not actually used to do work, like a game of ping pong, but no points are scored.
Wow, that's wild.
It is. And it actually has big implications in the real world, like in power grids. Low power factor means energy losses, inefficiency.
So you got to keep that power factor up.
Exactly. And power companies, they use things like capacitors to correct the power factor, to compensate for the effects of inductors and stuff.
Okay, that makes sense. So power factor, it's not just some theoretical thing. It's about making sure we're using energy wisely.
Could agree more. And speaking of using energy wisely, I think it's time we talk about transformers, those big guys you see on power line.
Oh, yeah. Can't miss them. I know they change voltage, but how do they actually, do it?
It's all about mutual induction. A changing current in one coil, it creates a current in another coil. Magnetic magic.
A magnetic handshake between coils, huh?
I like that. The source has a good diagram showing the primary and secondary coils all wrapped around a core.
Right. And depending on how many turns each coil has, you can either step up or step down the voltage.
Exactly. Step-up transformers, they boost the voltage for long-distance transmission. Less energy loss that way.
Clever.
And then step-down transformers, they bring it back down to safe levels for our homes. It's a brilliant system.
Yeah, it is, but they're not perfect, right? The source mentioned energy losses.
Good point. No such thing as a free lunch, right? There's always some loss. Things like flux leakage, eddy current.
Flux leakage,
Yeah.
eddy currents. I'm not sure
So flux leakage, it basically means not all of the magnetic field from the primary coil actually reaches the secondary coil. Some of it escapes, so to speak.
So it's like some of the energy gets lost along the way.
Exactly. And eddy currents, those are little currents that get induced in the iron core itself because of the changing magnetic field.
Yeah. Okay.
And those eddy currents, they generate heat, which is wasted energy.
So we're losing energy to heat inside the transformer itself.
Yep. And there's also hysteresis loss, which is related to magnetizing and demagnetizing the core over and over as the AC current changes direction.
Sounds complicated.
It is. But the main point is, even though transformers are incredibly useful, they're not 100% efficient.
Makes sense. Nothing is, I guess. Well, this has been a fantastic deep dive. We've gone from the basics of AC to resistors, inductors, capacitors, power factor, and now even transformers. I feel like I'm starting to see AC as this fundamental force that's behind so much of our modern world.
It is, and there's so much more to explore. But I think we've covered some of the key highlights from this beast of a PDF you sent.
We've definitely tackled the main ideas. But there was one last thing I was curious about mentioned in the source. LC oscillations. Any chance we could squeeze that in? LC oscillations. All right.
I got to be honest, that sounds a little mysterious.
Yeah, it's kind of cool, actually. It's all about how inductors and capacitors play together. Like their energy kind of bounces back and forth. Can you break that down a little more, what's actually happening?
Sure. So picture this. You've got a capacitor, fully charged up, and you connect it to an inductor.
All right, got my capacitor, got my inductor, they're connected. Go on.
So at the start, all the energy is stored in the capacitor, right?
Mm-hmm.
In its electric field.
Electric potential energy, right, like we talked about before.
Yeah, exactly. But as soon as you close that circuit, the capacitor starts to discharge. Current starts flowing through the inductor.
And the inductor's like, nope, not so fast.
Exactly. It resists that change in current. And all that energy, it gets stored in the inductor's magnetic field.
So the energy goes from the capacitor's electric field to the inductor's magnetic field. Okay, I'm following so far.
Good. Now the fun part is, it doesn't just stop there. That magnetic field in the inductor, it builds up and then it starts to collapse. And when it collapses, it induces a current that charges the capacitor back up. But with opposite polarity this time.
Opposite polarity. So it's like it's going in reverse now.
Exactly. And then the whole cycle repeats. Energy goes back and forth, capacitor to inductor, inductor to capacitor.
So it's like an energy ping pong game.
That's a great way to think about it. And the source, it actually compared it to like a block attached to a spring oscillating back and forth.
Ah, yeah, like a classic physics example.
Exactly. And just like that block and spring have a natural frequency, an LC circuit does too. It depends on the values of the inductance and the capacitance. And guess what? This natural frequency, it's analogous to the resonant frequency we were talking about before.
Wait, really? So resonance, it's not just about those LCR circuits. It's a more general concept.
Yeah, resonance is everywhere. Any system that can oscillate, it has a natural frequency, a pendulum, a spring, even these electrical circuits. And they all like to vibrate at that frequency. It's like their happy place.
So LC oscillations, they're kind of fundamental then.
They are. That's why they're so important in things like oscillators and filters. Think radios, computers, all sorts of technology.
Wow, that's pretty amazing. So this back and forth energy exchange, it's the basis for a lot of stuff. But the source did mention that it's kind of an idealized scenario, right? In the real world, there are losses.
Yeah, that's true. Resistance in the circuit, it'll cause the oscillations to die down eventually, just like friction slows down a swinging pendulum.
Nothing's perfect, I guess.
Right. But even then, the concept is super valuable. It helps us understand the underlying principles.
All right, I can get that. Theory and practice, they don't always match up perfectly. But understanding the theory helps us make sense of what's happening in the real world.
Well, I think we've covered an incredible amount of ground in this deep dive. From the basics of AC all the way to LC oscillations, it's been a real journey.
It has been. And AC, it's not just some abstract concept. It's literally the force that powers our modern world. Yeah, and with renewable energy becoming more and more important, understanding these AC principles, it's more relevant than ever. So to everyone listening, thanks for joining us on this deep dive into alternating current. I hope you found it as fascinating as we did.
And if you want to learn more, there are tons of resources out there. Textbooks, online courses, even hands-on experiments. Just, keep that curiosity flowing.
Couldn't have said it better myself.
Yeah.
Until next time, stay charged up,